Hello everyone. In this video tutorial, I'm going to show you how to use an ultrasonic rangefinder to control a servo motor. This is going to be most applicable in your project for functions like doors that are going to open automatically when someone gets close enough to that sensor on your project. So the first thing that I want to show you is the diagram, the pictorial diagram that I've created on Tinkercad. And I also would like to explain a little bit about the ultrasonic rangefinder because I do think that it's pretty important. So an ultrasonic rangefinder is going to emit an ultrasound of about 40,000 hertz, which is going to travel through the air. And if there's some sort of object or obstacle in its path, then that signal is going to bounce back to the module. What the rangefinder is going to do is consider the travel time and the speed of sound, and then it's going to calculate the distance automatically, and this is going to happen very rapidly over and over. On our larger rangefinders that we used earlier in the course when we were studying kinematics, you could really hear the clicking, and here you're not going to be able to hear that. But that is still the process that is taking place. I have established this diagram in Tinkercad because not only can we look at the diagram and the wiring in Tinkercad and discuss it a little bit, but we can also open up this function, which is a coding function. Some of you might not know that once you write code in Tinkercad, if everything is wired correctly, you can start a simulation and it'll actually show you if all of the functionalities you were hoping for work. There's also a neat little tool here that allows you to use some block code if you're really having some trouble getting started, and so that and then it will later convert it into text. Obviously for today, I'm going to just show you how to use that code function and not the block code, but it is there. It's available as a resource for you if you absolutely need it. All right, so wiring this rangefinder is a pretty straightforward thing. The rangefinder has a ground, a VCC, and the ground and the VCC, the ground's just going to go right into the negative, which is attached to the ground. The VCC will go into the positive, which is attached to the 5-volt pin on the Arduino board. And then the trigger and echo pins, which I'll explain a little bit more about later, can connect to any digital input-output pin on the Arduino board. So let's step over to the code here, and I'm just going to get started with the code. When you're including a servo motor, you're going to need to actually call that out as your first line of code. Oops. So I'll need to say include, and then I'll need to say servo.h. I'll go to the next line and write servo. I'll just call it out. This just means that I'll be including just a single servo here. I'll initialize some of these variables, trig pin, which is just the trigger pin on that ultrasonic rangefinder, and I'll tell it that it's at 10 because as you can see, we have wired the trigger pin into D10 right here. Because it's digital, we don't need to put that D. We're going to tell it that the echo pin is 13, and then we're going to call out a couple of other variables like distance and duration, which do need to be called out in this manner, and they're two variables that we're going to use later and store information to. So obviously, once I get down to the bottom of the code where we're really dealing with this ultrasonic rangefinder, I'll be very clear as much as I can about each line of code and what it's doing, what its function is. All right, so now that we have called all our variables out that we're going to need for this program, we want to use the setup, and in our setup we're going to attach the servo to a particular pin in this case. The servo motor, I'm just going to close the code for a second. You can see that the servo just drops right into the digital pin 3. So if we open up our code again, here we're attaching the servo to pin 3. And now I'm going to use pin mode. And this is something hopefully you should be familiar with, just declaring these inputs and outputs. The servo has already sort of been declared as the thing here in the setup, and so we don't need to really cycle back to it. But I'm going to say that the trigger pin is an output, and that the echo pin is an input. And I'm going to close that out now. And now we're going to step into our loop. And this is where things will get a little more confusing, but I'll do my best to explain. So this first piece, servo 1 dot write, this is basically just writing information to the servo, and this is basically it's telling it the rotation and where it should be at all times. When we put a 0, that indicates a 0-degree rotation. Now we're going to give it a conditional statement, which is if distance is less than or equal to, let's say, let's give it a close distance, so 10 centimeters. Like if somebody gets 10 centimeters away from this door, we wanted to trip and activate the rotation of the servo. And then we're going to go to the next line and we'll tell the servo what to do. So if, let's say we want the servo to rotate 180 degrees, we'll write this servo 1. And again, like you see that this function for actually rotating the servo is a little bit different than anything we've seen. We'll rotate it 180 degrees and then we'll close out that conditional. Now these digital write statements, I'll put them in here and I'll try my best to explain. So in order to generate the ultrasound, you're going to need to set the trig pin or the trigger in a high state for a certain amount of time. And that's going to send out that sonic burst, or that emission of sound that's going to travel and be received in the echo pin. The echo pin is then going to output the time in microseconds that the sound wave traveled. And so there's this process of sort of pulsing that trigger pin and getting that reception from the echo pin. So the trigger pin needs to be set to high to emit that signal. The echo pin then needs to be set to high to receive it. And then obviously there needs to be some sort of conversion that happens where we're making a conversion of that duration of time to the distance. And I'll give that a little explanation of that as well. But in order to make this all happen, right, in order to have it send the signal out and receive the signal back and then make that conversion, we have to do a digital write. So we'll digital write the trig pin to low. We'll then digital write the trig pin to high. So this is the emission of that signal for a certain period of time. You want this duration to be equal to pulse in, echo pin, and the echo pin is going to then become high to receive the signal, and then we're going to store that value, whatever it is, to duration. So I'll add in just a short delay in this process as well, which for this particular purpose in this particular program, it shouldn't really have much of an effect. But anyway, this next piece is pretty crucial. So like I said, what this ultrasonic rangefinder is doing is it's taking some amount of time and then it's converting it to a distance based off of the speed of sound. And so the distance is, and this is all physics that we've learned, is the duration times 0.034 over 2. And you might be looking at this thinking, well, where the hell did you get that number? But it's really not so difficult to determine if you look at this, right? You notice 30.034 is very similar to something that you might be familiar with, which is the speed of sound. And if you're not familiar with it, that's also okay. But if we think about how to find the distance, right? If we know that velocity equals distance divided by time. This is not part of the program, by the way. I'm just kind of walking you through this. Then we can make a manipulation to get the distance, which is going to be the velocity times the time. So velocity times time is going to equal the duration. I'm sorry, is going to equal the distance. I'm sorry, we're dealing with distance and duration is really the time, right? So this is the distance equals the time times the velocity. And you might be looking at this thinking, okay, I don't really understand how this is the velocity. But in general, we're actually dealing with we're not dealing with meters per second. We're actually dealing with microseconds here. And so that's why you get this strange conversion, because the speed of sound in air is actually around 340 meters per second. And so the speed of sound in air would be 0.034 meters per microsecond, if that makes any sense. So we're going to get rid of all of this. And what you'll notice, if you get rid of the code here, like you don't actually have to get rid of the code. But if you start the simulation, oops. What did I do here? Okay, that was funny little debugging in the moment there, and sometimes that'll happen to you as well. But I had a lowercase w there, and hopefully once I start the simulation now, it should do. So as you can see, right, the servo motor is moving because I am less than 10 centimeters away. And it's going to rotate a full 180. Now, if I wanted to move back, let me put it all the way back here, right, to 40.9 centimeters, so it's further away. And so now it's going to go back to its default position, which was 0 degrees. Now, if I'm like, I change my mind and I want it to go back, I will put it closer. And here, like, things have really slowed down. It's not actually going to be this slow. So the next step, obviously, is to affix something to this, this piece here that comes off of the servo motor. I have an example of that I've created, and basically all you need to do is take a piece of cardboard and fold it at the bottom, and then just tape it onto this part of the motor. Obviously you want the edge of the door to start here, and the door can come off in this direction, or it can start here and come off in this direction. But then the servo motor itself, this portion here, is going to need to just be mounted in the inside. So you can either sweep the door open or closed. I will do a little quick demonstration so that you can see the mechanics of how I put it together. And I think that is all I have for you in terms of the pictorial and the coding, and I hope that it was really helpful.
And you used like a